Hey there, Calc 3. So, this video is kind of casual. We're going to talk about mass and center of mass, and that's it. We're not going to do a whole lesson on anything. It's just, hey, here's another application of multiple integrals. Honestly, it's kind of a cool one. So, we're going to find mass and center of mass of what's called a lamina, which is basically kind of like, I don't know, this. This is a lamina, okay? It's kind of like something that's two-dimensional, but you can hold it in your hand, I guess is how I would most accurately describe a lamina. All right, something that's kind of like a sheet of uniform thickness. So if we wanted to find the mass of a planar lamina of variable density, all right, you just take the double integral of the density function, because density obviously has a lot to do with mass. And so let me talk about what this really means. So it says find the mass of the triangular lamina with vertices at 0, 0, 0, 3, and 2, 3. If the density function is rho equals 2x plus y, that curly p thing is called rho, R-H-O, BT dubs. So rho is 2x plus y. In other words, if you're in the first quadrant, the further you get from the origin, the more dense it is. So if I thought about like shading this with respect to density, when I get up to the top, it's really dense. And then less dense and less dense and less dense and down to that. Okay, so if I thought about the density of this thing, and the x seems to affect the density more than the y, so it'd probably be denser like over here, the bigger the x is. Okay, so I don't know, something like this maybe? It's not a great answer, but okay. Now, if I want to find the mass of that thing, I just have to throw that density function inside a double integral. So I'm going to have the double integral of my region for the integrand 2x plus y. Well, 2x plus y is integrable with respect to x and y equally. So I'm going to do dy dx because this region is vertically simple. So I'm going to call that dy dx. This would be the line y equals 3. That would be my top curve. And if this is the point 2, 3, and it passes through the origin, this is y equals 3 halves x, so that would be my bottom curve, top to bottom. And then my x goes from 0 to 2. So I'm going to evaluate this with respect to y, 2xy plus 1 half y squared from 3 halves x to 3. The integral from 0 to 2 of, let's see, that would be 6x plus 9 halves minus, all right, if I put 3 halves x in for y, that's going to be 3x squared. And if I put 3 halves x in for y and then square it, that's 9/4, 9/8 x squared. And then I'm evaluating that with respect to x. I'm going to use my calculator off to the side because it's quicker than the one that I can pull up on the screen. Let's see, math 9, 0 to 2, 6x plus 9 halves. How's everybody doing today? Everybody having a good day? I'm having an okay day. My computer keeps doing weird things, which is definitely not ideal, but I deal with it because I have to. Okay, assuming I typed that incorrectly, I got a very nice mass of 10. Okay. Now, the power behind that is, yeah, you got mass now. Good for you. What if you wanted to balance that thing on your finger? What if you wanted to find the center of mass? If you want to find the center of mass, what you need to do is figure out how far from each axis your finger needs to be. So to figure out how far your finger needs to be away from the x-axis, you multiply rho by y and then reintegrate. To figure out how far from the y-axis you need to be, you multiply by x and then integrate. And then the center of mass is going to be those two values divided by the mass. And that gives you the coordinates. All right, now, my language didn't really make a whole lot of sense, but basically, if you want the x coordinate for the center of mass, you just throw an x in front of rho. If you want the y coordinate for the center of mass, you throw a y in front of rho, okay? Because y is from mx, which is here, and x is added to my, which goes there. And if you're thinking, wait, Mrs. Weber, why didn't they just call them my and mx and make the subscript match the variable? And the short answer is, I got to be honest, they probably should have. But the long answer is your moment with respect to the x-axis is what this m stands for. And it means how far away from the x-axis would you need to put a sword so that you could balance the triangle on the sword. And your distance from the x-axis, I wish I could show you. I can show you. I need a marker. I got a marker. Here we go. If I wanted to balance something at a distance away from the x-axis, that thing would cross through the y-axis. Okay. So that's why there's the confusion about mx and my. And it's really your moment with respect to the x-axis is a y coordinate. All right. But anyways, I'm just rambling at this point. Let's, do it. So find the center of mass of the lamina. So I am going to do the double integral. And the fun part is I just have to multiply by x and y. So I have 2xy times x. 2x plus y times x. And then I have 2x plus y times y. And when I distribute that x and when I distribute that y, it's not going to make this any harder to integrate. So I'm going to stick with dy dx on both of these. And then I'm also going to get to keep my region on both of these, which was 0 to 2 for x and 3/2 x to 3 for y. All right. So I'm going to do that thing right now where I am going to just shut up and evaluate this and not talk my way through it. So take a second and evaluate both of those. So I got 8.5 and 22.5 as my moments. And so I'm going to take those and divide them by the mass and get my center. So the thing that got multiplied by x is going to help me get my x coordinate. So my center is going to be 8.5 divided by 10 and 22.5 divided by 10, which gives me a center of mass of 0.85, comma 2.25. Now let's see if that makes sense. So 0.85 and 2.25 would be over here and right up there. And it's saying if I put my finger there, it should balance. Now, does that make sense? I think that it does, because I'm putting my center of mass in with the more dense area of it. Okay, that's definitely not the center of the triangle, but given that this triangle doesn't have uniform density, I can believe that my center of mass would be right there. All right, that's it. We got through this last page. Hurrah, hurrah. And yeah, we're done. So hopefully you understand now applications of double integrals. After this video, we have then done mass, center of mass. Prior to this, we did average value, and I don't know, we did something else. What else did we do? That's average value. Oh yeah, and surface area. Okay, are there more applications of double integrals? Of course there are. But this is just a couple cool ones in context. I'm done. Toodaloo. See you later.